Before we dive in, one honest clarification. The images we're about to discuss weren't captured in Cassini's literal final hours before it burned up in 2017. They were taken during the closing years of its extended mission in late 2010 and early 2011, when Cassini caught something happening on Saturn that no spacecraft had ever witnessed up close before. Some of the most detailed, most scientifically important images this spacecraft ever captured turned out to come not from its very last transmission, but from this specific unrepeatable event that unfolded mid-mission. In this video, we're going to walk through exactly what Cassini saw, why it upended long-standing assumptions about Saturn's atmosphere, and why scientists are still analyzing the aftermath of this event years later. If you enjoy real documented space science rather than exaggerated claims, stick around till the end. It's worth being upfront about why this distinction matters, rather than just quietly glossing over it. Cassini's mission spanned 13 years at Saturn, and across that entire span, different phases of the mission produced genuinely important discoveries. The very last images, captured in September 2017, are their own separate story, one we've covered elsewhere. But treating final images loosely to mean some of the most consequential images from Cassini's later years, rather than its literal last hours, is exactly how this particular discovery gets described in most accurate reporting, and it's worth understanding why this event earned that reputation. Let's start with the basics of what actually happened. On December 5, 2010, a small, bright convective storm cloud erupted in Saturn's northern hemisphere near 38 degrees latitude. At first, it didn't look particularly remarkable, just a modest bright spot against Saturn's typically calm, hazy, pale yellow atmosphere. But within about 2 weeks, that small storm had exploded outward, covering an area of roughly 60 million square kilometers, and it kept growing from there. Amateur astronomers around the world using backyard telescopes were actually among the first to spot and track the storm's initial outbreak. And within about 50 days, the storm's bright, churning tail of clouds had wrapped entirely around Saturn's northern hemisphere, forming a continuous band that encircled the entire planet. The role amateur astronomers played in this story deserves genuine recognition. Long before Cassini's own dedicated observation campaign fully ramped up, it was Earth-based amateur observers tracking Saturn from their own backyards with modest telescopes who first caught the storm's initial outbreak and began documenting its rapid early growth. This kind of collaboration between professional spacecraft missions and amateur astronomers has become an increasingly valuable part of planetary science, with amateur observers often providing continuous, high-frequency monitoring that complements the more occasional but far more detailed observations a spacecraft like Cassini can provide during its scheduled observation windows. This event became known as a Great White Spot, a name chosen by analogy to Jupiter's famous Great Red Spot, though the two features are actually quite different in nature. Unlike Jupiter's Great Red Spot, which is a long-lived, relatively stable anticyclonic storm that has persisted for centuries, Saturn's Great White Spots are much rarer, much more explosive, short-term convective outbursts. Since detailed telescopic observation of Saturn began, astronomers have only documented 6 of these events, going all the way back to 1876. That works out to roughly one great white spot appearing every 30 years or so, which happens to line up closely with the length of a single Saturnian year, since Saturn takes about 29.5 Earth years to complete one orbit around the Sun. This timing wasn't considered a coincidence. Scientists had come to associate these storms with Saturn's seasonal cycle, specifically believing they tended to erupt during the northern hemisphere's summer season. Every previously documented great white spot had followed this same general pattern, appearing at a similar point in Saturn's seasonal calendar. This made the timing of the 2010 storm genuinely startling to researchers who had been expecting, based on this established pattern, that the next great white spot wouldn't appear for years yet. Instead, this storm erupted roughly a full decade earlier in Saturn's seasonal cycle than the historical pattern would have predicted, catching planetary scientists by surprise before the storm had even finished growing. What made this particular great white spot truly unprecedented, though, wasn't just its surprising timing. It was the fact that, for the very first time in recorded history, a spacecraft was actually there, in orbit, with a full suite of modern scientific instruments ready to observe one of these massive storms unfold in real time and in extraordinary detail. Every previous great white spot in the historical record had only ever been observed from Earth using ground-based telescopes limited by distance, atmospheric interference, and comparatively modest resolution. Cassini's presence at Saturn during this exact storm meant scientists could, for the first time, study a great white spot with close-range imaging, infrared spectroscopy, and radio and plasma wave instruments simultaneously, all pointed at the same unfolding event. Cassini's cameras began capturing images of the storm almost immediately after its outbreak in December 2010, and its visual and infrared mapping spectrometer captured its first detailed spectra of the storm by February 2011. What these instruments revealed went far beyond anything ground-based telescopes alone could have shown. The storm's convective head, essentially its actively churning leading edge, grew to cover an area of roughly 60 million square kilometers within just its first 2 weeks, and it moved westward across Saturn's atmosphere roughly 10 meters per second, faster than the surrounding background winds, creating a widening trail of bright clouds stretching out behind it as it raced around the planet. By the time scientists analyzed the storm's full extent, they realized it had become large enough to potentially swallow the entire planet Earth, with room to spare. The storm's leading edge alone extended over 10,000 kilometers at cloud top level, and as it continued developing, it produced an enormous planet-encircling disturbance affecting the entire latitude band between roughly 25 and 48 degrees north. Cassini's imaging system recorded wind speeds within the storm's head reaching up to 160 meters per second, organized into what scientists described as a divergent, open anticyclone, where massive cumulus-like cloud clusters interacted with the surrounding atmospheric flow to generate a distinct storm front, not unlike the leading edge of a massive terrestrial thunderstorm system just operating on a genuinely planetary scale. One of the most dramatic aspects of this storm, and something Cassini was uniquely positioned to detect, was intense lightning activity. Cassini's radio and plasma wave science instrument picked up electrostatic discharges consistent with lightning strikes occurring within the storm's clouds, continuing intermittently over the course of several months. This gave scientists a genuinely rare opportunity to study lightning activity on a gas giant in this kind of sustained detail, comparing it against similar, though far less energetic, lightning phenomena observed on Earth and on Jupiter. The storm's lightning activity didn't stay constant throughout its lifespan. It intensified, fluctuated, and eventually became increasingly sporadic as the storm approached the end of its active phase, giving researchers a detailed timeline of how convective lightning-generating activity evolves over the full life cycle of a planetary-scale storm system. Detecting lightning on Saturn is genuinely difficult from Earth, since the planet's distance and its comparatively hazy upper atmosphere make it hard to visually spot individual lightning flashes the way you might on Jupiter. Cassini's radio and plasma wave instrument got around this limitation by detecting the electromagnetic signature lightning produces rather than relying on visual detection alone, allowing scientists to track the storm's electrical activity even when the flashes themselves weren't easily visible in standard camera images. This approach revealed that the storm was producing lightning strikes far more frequently and over a far longer sustained period than any previously studied Saturnian storm, reinforcing just how energetically unusual this particular event turned out to be compared to typical atmospheric activity on the planet. The storm continued developing and expanding for an extraordinarily long time. By the time its most active phase concluded around June 2011, it had lasted roughly 200 days, making it the longest documented great white spot storm in the entire historical record, easily surpassing the previous record holder, a similar storm documented in 1903 that lasted about 150 days. The storm's eventual end came about in a genuinely dramatic fashion, the fast-moving head of the storm having raced all the way around Saturn's entire circumference, eventually caught up to and collided with its own slower-moving tail, essentially lapping itself. This collision between the storm's head and its own trailing vortex appears to have been what ultimately terminated most of the storm's active convective behavior, with lightning strikes becoming sporadic and the storm's brightest cloud features gradually fading away. Now here's where the story moves from simply being an impressive, record-breaking weather event and into genuinely rewriting scientific understanding of how Saturn's atmosphere actually works. While the visible storm at cloud top level eventually settled down by mid-2011, Cassini's composite infrared spectrometer detected something that nobody had previously observed in connection with any of these storms. The effects of the storm hadn't stayed contained at cloud level at all. They had propagated upward into Saturn's stratosphere, creating warm, persistent air masses at altitudes far above where the visible storm clouds themselves were located. Scientists nicknamed this stratospheric disturbance the beacon, and it turned out to be an almost startlingly long-lasting phenomenon. This stratospheric warming, detected at pressure levels corresponding to altitudes well above the storm's visible cloud tops, showed localized temperature increases of roughly 60 Kelvin above the surrounding stratospheric background temperature. An enormous jump for a planet where atmospheric temperatures are normally remarkably stable and slow to change. Follow-up observations using both Cassini's own instruments and ground-based infrared telescopes confirmed that this beacon of stratospheric warming persisted for well over a year after the visible cloud-level storm itself had already faded away, gradually cooling and dissipating over an extended period that stretched into 2012, and, according to some of the longer-term studies, even beyond. To put that 60 Kelvin temperature spike in perspective, that's roughly equivalent to a 108-degree Fahrenheit jump in a region of Saturn's atmosphere that would normally change by only a few degrees over the course of months or even years under undisturbed conditions. Researchers track this warm region, sometimes described as having a vertical structure resembling a beacon or a tower of unusually warm air extending upward through multiple layers of the stratosphere using detailed spectroscopic measurements that could pinpoint both the temperature and altitude of the disturbance with remarkable precision. A study using Cassini's composite infrared spectrometer identified a specific persistent warm air mass centered around a pressure level of roughly 2 hectopascals, later confirmed and further refined by independent ground-based observations conducted in July 2011, roughly a month after the visible storm's most active phase had already concluded. This finding fundamentally changed how atmospheric scientists thought about the relationship between Saturn's lower, cloud-forming atmosphere and its much higher stratosphere. Before this storm, these two layers were generally treated as largely separate systems, with limited, poorly understood interaction between the two. The Great White Spot's stratospheric aftermath demonstrated, in unmistakable detail, why that a sufficiently powerful convective storm at cloud level could inject enough energy and disturbance into the atmosphere to meaningfully alter conditions in the stratosphere far above, for well over a year after the original storm itself had already ended. This kind of vertical coupling between atmospheric layers, while somewhat expected in theory, had never been documented with this level of detail and persistence on any gas giant planet before. The storm's effects weren't limited to just temperature changes either. Cassini's spectrometers also detected significant, unexpected changes in the chemical composition of Saturn's atmosphere in the region affected by the storm. Researchers analyzing data from Cassini's visual and infrared mapping spectrometer found evidence of ammonia, ice and water ice, being lofted upward by the storm's powerful convective activity, materials that under normal undisturbed conditions would typically remain confined to much deeper layers of Saturn's atmosphere, well below where Cassini's instruments could usually detect them from orbit. The storm's violent upward convection had effectively dredged up material from deep within the planet's atmosphere and carried it high enough to become detectable from space, giving scientists an unprecedented, if temporary, window into the composition of Saturn's deeper atmospheric layers. This detection of ammonia ice in particular carried significant scientific weight. Under Saturn's normal atmospheric conditions, ammonia ice clouds are believed to form deep within the atmosphere, well beneath the visible cloud tops that Cassini's cameras typically photograph. Directly detecting ammonia ice at higher, normally inaccessible altitudes gave scientists rare, direct evidence supporting theoretical models of Saturn's deep atmospheric structure and cloud layering, models that had previously relied largely on indirect inference and comparison with Jupiter's somewhat better studied atmosphere, rather than direct observational confirmation from Saturn itself. Beyond the ammonia and water ice, scientists also documented unusual excesses in stratospheric hydrocarbon compounds in the region disturbed by the storm, along with broader disruptions to the normal chemical and thermal structure of Saturn's upper atmosphere. Follow-up studies using ground-based infrared telescopes, including detailed spectroscopic observations conducted in July 2011, roughly a month after the storm's active phase had ended, confirmed and further refined these findings, mapping out the vertical structure of the stratospheric warming with increasing precision and tracking exactly how it continued evolving as the disturbed region gradually cooled back toward its normal state over the following months and years. All of this combined evidence forced planetary scientists to substantially revise their understanding of just how disruptive and how far-reaching a single storm event on a gas giant planet could actually be. Before Cassini's detailed observation of this event, models of Saturn's atmosphere generally treated major storms as comparatively localized, cloud-level phenomena, with limited lasting impact on the broader atmospheric system. Once the visible storm activity subsided, the 2010 to 2011 Great White Spot demonstrated instead that a single storm event could meaningfully disturb the planet's atmosphere across an enormous range of altitudes, injecting energy and material that persisted and continued evolving for well over a year after the original visible storm had already faded from view. This also connects to a broader mystery scientists are still working through. Why did this particular storm erupt roughly a decade earlier in Saturn's seasonal cycle than every previously documented example? Researchers have proposed several possible explanations, though no single fully confirmed answer has emerged. Some studies suggest the timing might relate to how deep water clouds, believed to exist far below Saturn's visible cloud tops, gradually accumulate moisture and instability over long periods between storm events, eventually triggering convective outbursts once certain conditions are met, rather than strictly following a fixed seasonal calendar. Other researchers have pointed to the possibility that Saturn's deep internal heat flow, or subtle variations in atmospheric composition at different depths, could play a larger role in triggering these storms than previously assumed, potentially decoupling their timing somewhat from purely seasonal sunlight patterns. But though this remains an active, ongoing area of research, and the unusual timing of the 2010-2011 storm is part of why scientists continue studying archived Cassini data from this event, hoping to better understand what actually triggers these massive, periodic disturbances. This uncertainty around timing has genuine practical implications for how scientists plan future observation campaigns. If great white spots really do follow a strict, predictable seasonal pattern, mission planners and ground-based observation teams could schedule dedicated monitoring campaigns years in advance, confident about roughly when the next storm should appear. But the 2010-2011 storm's unexpectedly early arrival undermined that confidence considerably, suggesting that whatever combination of deep atmospheric processes actually triggers these events is more complex and less predictable than the historical pattern alone would suggest. This means astronomers today have to maintain more continuous, less schedule-dependent monitoring of Saturn if they want any reasonable chance of catching the next great white spot from its very earliest stages, rather than assuming they have decades of advance warning before the next one is due. It's also worth appreciating just how valuable it was, scientifically speaking, that Cassini happened to already be in orbit when this specific storm erupted. Given that these great white spot events occur roughly once every 30 years, and that Cassini's mission at Saturn lasted only 13 years, there was no guarantee at all that a storm of this magnitude would occur during the spacecraft's operational lifetime. Mission planners couldn't have designed Cassini's instruments or timed its mission specifically around catching this kind of rare event. It was, in a very real sense, a fortunate coincidence of timing that placed a fully capable orbiting spacecraft in exactly the right place at exactly the right moment to observe something that might not happen again for another 3 decades. Consider the alternative scenario, one that easily could have happened instead. If Cassini's mission had ended just a few years earlier, or if the Great White Spot had erupted just a few years later, humanity's only record of this entire historically significant weather event would have been comparatively limited ground-based telescope observations, similar in quality to how every previous great white spot throughout the 19th and 20th centuries had been documented. The stratospheric beacon discovery specifically, along with the detailed lightning data and the direct detection of ammonia and water ice being lofted by the storm, all depended entirely on having sophisticated orbital instruments in place at the exact right moment. None of that level of detail would have been possible from Earth alone, no matter how good ground-based telescope technology becomes. This element of scientific luck is worth sitting with for a moment because it highlights something important about long-duration space missions generally. Cassini wasn't specifically designed or funded with the expectation of catching a great white spot storm. Its extended mission simply happened to overlap with the natural, roughly generational timing of these events. This is part of the broader argument mission planners often make for extending flagship missions well beyond their original planned duration whenever the spacecraft remains healthy and capable. You genuinely can't predict in advance what rare, significant events a longer duration mission might happen to catch, and the 2010-2011 Great White Spot stands as one of the clearest examples of exactly this kind of unplanned scientific windfall. Let's also consider how this discovery connects to the broader question of understanding gas giant atmospheres in general, extending beyond just Saturn itself. Jupiter's Great Red Spot has been studied for centuries as a stable, long-lived storm system, giving scientists a very different kind of atmospheric case study compared to Saturn's much more explosive, short-lived Great White Spots. Having detailed, close-range data on both types of atmospheric phenomena, a long-lived stable storm on one gas giant and a short, violently disruptive storm on another gives atmospheric scientists valuable comparative data points for building and testing general models of how convection, energy transport, and atmospheric chemistry work across gas giant planets more broadly, including gas giant exoplanets discovered around other stars, where directly observing individual storm systems in this kind of detail remains far beyond current technological capability. Let's address a few common questions people tend to have about this event. Could a storm like this happen again soon, or are we due for another great white spot? Based on the roughly 30-year historical pattern, the next expected great white spot would traditionally be anticipated sometime around the 2040s, following the standard seasonal timing. However, given that the 2010-2011 storm broke from this pattern by occurring roughly a decade early, and given that scientists still don't fully understand what triggers these events, predicting the exact timing of the next occurrence remains genuinely uncertain. Is there currently a spacecraft in position to observe the next great white spot if it happens? Not currently. Cassini's mission ended in 2017, and no dedicated Saturn orbiter mission is currently active or funded to replace it. If another great white spot erupts in the coming years or decades, scientists would likely need to rely primarily on ground-based telescopes and space telescopes like Hubble or James Webb for detailed observation, rather than a spacecraft in close orbit around Saturn itself, unless a new dedicated mission is developed and launched before then. Why don't we see similar storms on Saturn more often, given how large and dramatic this one was? Saturn's atmosphere most of the time is remarkably calm and stable in comparison to more turbulent worlds like Jupiter, with comparatively bland, muted cloud bands visible under normal conditions. Scientists believe this relative calm reflects deep, slow-building atmospheric processes, potentially related to moisture and instability gradually accumulating in deep-water cloud layers over long periods that only occasionally reach a tipping point capable of triggering an event as large and disruptive as a great white spot, rather than smaller-scale storms occurring more continuously the way they do on some other planets. Did the storm cause any permanent, lasting changes to Saturn's atmosphere? Some effects lingered for well over a year, particularly the stratospheric beacon warming and associated chemical disturbances, but current evidence suggests Saturn's atmosphere eventually returned to something resembling its normal pre-storm baseline state once the disturbance had fully dissipated. However, because scientists are still analyzing archived Cassini data from this event, some subtler or longer-term effects may still be under active investigation. How does this storm compare to storms observed on other planets in our solar system, like Neptune's Great Dark Spot or Jupiter's various storm systems? Each of these atmospheric phenomena is genuinely distinct in character. Jupiter's Great Red Spot is remarkably long-lived and stable, persisting for centuries. Neptune's Great Dark Spot, observed by Voyager 2 in 1989, turned out to be a comparatively short-lived feature that had actually disappeared by the time Hubble observed the planet again just a few years later. Saturn's Great White Spot sits somewhere in between, dramatic and explosively energetic, like a short-term event, but recurring on a remarkably regular generational timescale, unlike anything documented on the other gas giants. Studying all of these different storm types together gives scientists a broader, more complete picture of just how varied atmospheric behavior can be across gas giant planets, even within the relatively small sample size of worlds in our own solar system. So, to bring this all together, what did this event actually rewrite about our understanding of Saturn? It showed that Saturn's massive periodic great white spot storms don't strictly follow the seasonal timing pattern scientists had confidently assumed based on historical records, catching researchers off guard by erupting roughly a decade earlier than expected. It revealed, for the first time in this kind of vivid detail, that a single storm's effects can propagate far beyond the visible cloud layer, disturbing Saturn's stratosphere with persistent warming and chemical changes that lasted well over a year after the original storm had already faded from view. And it gave scientists an unprecedented close-up look at lightning, wind dynamics, and atmospheric chemistry during an event type that historically could only ever be studied from the comparatively limited vantage point of Earth-based telescopes. Cassini didn't just happen to be present for this storm. It turned what could have been just another distant, blurry observation from Earth into one of the most detailed atmospheric case studies ever conducted on any gas giant planet, human or robotic, in the history of planetary science. And because this specific combination of circumstances, a fully capable orbiting spacecraft present during one of these rare, roughly generational storms, may not happen again for decades, the data Cassini gathered during this single, unrepeatable event continues to serve as the primary scientific reference point for understanding exactly how these massive, planet-encircling storms actually work. It's worth ending on the same honest note we started with. This wasn't Cassini's literal final transmission, and the storm wasn't captured in the spacecraft's dying moments. But in terms of genuinely rewriting scientific understanding of Saturn, few observations from the entire 13-year mission carry as much weight as this one. Sometimes the images that change the most about what we know don't come from a dramatic final farewell. They come from a spacecraft simply being in the right orbit, with the right instruments, at exactly the right moment, ready to watch something extraordinary unfold that nobody could have scheduled in advance. If you found this breakdown interesting, make sure to like this video, subscribe to the channel, and let us know in the comments. Did you know Saturn's atmosphere could produce a storm large enough to swallow the entire planet Earth? See you in the next video with another real, grounded space story worth exploring.